I've been asked by yet another good friend of mine to help her with quantum mechanics and to start at the beginning. Well, here goes. If you wish to learn something from this planned series, I strongly suggest not to consume more than 1 or 2 of these videos per day and to frequently pause and do any of the presented calculations yourself, especially if you think you've understood what has been said. Mathematics has a very unique way of showing you just how much insight you are still missing. Also, please don't feel discouraged by this, it is absolutely normal. Any theory in physics starts with some assumptions, usually some axioms of mathematical nature. If the conclusions drawn from these assumptions coincide with experimental results, you begin to trust the theory at some point. In the case of quantum mechanics, which primarily describes the workings of very small objects, the axioms are a bit weird. Because of this, countless people have criticized and challenged it over the years, which is why it is now one of the best tested theories of all time. I will not formally introduce the axioms, because this is an introductory YouTube video after all. I will rather mention them in passing and focus on working with quantum mechanics. In classical mechanics, a particle is usually point-like, and it is described by its time-dependent position in 3-dimensional space. In quantum mechanics, it is described by a so-called wave function, which assigns every position and moment in space and time a complex number. The interpretation of this wave function is that the square of its absolute value gives you the probability density to find the particle at position r and time t. This is already weird. We do not know where exactly the particle is, we just know where it probably is. This, however, we can quantify. The probability to find the particle in a specific region, for example a box with edge lengths of 1, is given by the integral over the probability density. It is a very common theme in quantum mechanics that one can only ever talk about probabilities instead of certainties. The interpretation as a probability density has a consequence. You will certainly find the particle if you look everywhere in the entire universe, so the integral of the probability density over all of space should give you 1. Wave functions that fulfill this property are called normalized, and they are henceforth the only wave functions we accept as physical. Many functions can be normalized by dividing them by the square root of the result of this integral, but there is also quite a number for which this is not possible. The constant 0 function always integrates to 0, any other constant function to infinity, any polynomial to either 0 or infinity, and the integral of the cosine is not even defined. The condition of normalizability alone does not tell us much about the particle, we do not yet know how it behaves. In classical mechanics, this information is contained in the Newtonian equations. Quantum mechanics is governed by the famous Schrödinger equation. It reads I h bar temporal derivative of psi equals h psi. I don't know about you, but I think that this is one of the most beautiful equations in all of physics. It features the complex unit I, Planck's reduced constant h bar, a partial time derivative, and the Hamiltonian h. Mathematically speaking, h is a linear operator, meaning that it somehow affects anything that stands adjacent to the right of it, and does so in a linear manner, such that for any 2 wave functions psi and phi and any complex number c, h psi plus c phi equals h psi plus c h phi. Physically speaking, h is the energy of the particle or system. This energy depends on the environment and what the system looks like, and thus this is the part where physics enters the equation. The first step in any quantum mechanical calculation is usually guessing what Hamiltonian describes the system you wish to work with. This may sound a bit hand-wavy, but there are some reasonable starting points for Hamiltonians, and after a while you develop some intuition for what might be the correct description. If you know the wave function of a system at any time, the derivative in the Schrödinger equation tells you what will happen to it next. Conversely, a wave function describes the state of a certain system if and only if it is normalized and fulfills the Schrödinger equation for the corresponding Hamiltonian for all times. You might think that this is all rather abstract and that you would like to see an example now. Well, I think that it is time for a break, for both you and me, so I will postpone the example to the next video. Until then, enjoy life if you can, and don't be ashamed if you can't.